My name is Starzinger. I work for Google as a software engineer. I work on the V8 team, which is now totally based in Munich. So V8 is developed in Munich in the engineering office. And the purpose of this talk is basically twofold. One is performance, of course. We are all talking about performance. But the second point is the memory footprint that all the performance optimizations introduce. And so I want to give it a different spin from all the other talks that have been given about V8 and see how we can get both of best worlds. So great performance and low memory footprint. So before I head off into that, first a one-slide basic overview of how V8 works and kind of a reminder of what you might have already heard. So the main thing, there are a few things at Google that we know to be true, and one of those things is fast is better than slow. So obviously that's the main driving force for V8. We want to be the fastest JavaScript engine out there. How do we try to achieve that? So there are a few ingredients to that. One would be inline caching, which allows us to access properties of objects fast, because that's the main thing that all JavaScript applications do, manipulate objects, access properties. Then, as we heard in the previous talk, optimizing compiler to really kick ass at the hot methods. And also, another important ingredient, an efficient garbage collector. And we actually have a new GC. That's an incremental low-pause garbage collector. It's generational, and we try to get the pause times as low as possible by basically interleaving mutator work, so work that your application has to do, with garbage collection work. Slicing these up and interleaving it so that we can make progress with garbage collection as well as progress with your application. And a lot of other ingredients, we mix those up and steer them well, and hopefully get high performance characteristics in our engine. So we got speed, awesome. But what else did we get with that? Imagine you bought a new car and you know it has a pretty damn engine in there, and you want to take it out for a quick drive, and suddenly you find yourself in here. So you look around and see all the other cars and start thinking about, whoa, hang on, wait a second. What is the footprint of all of that? In your car, you might be worried about carbon footprint. If you're talking about JavaScript engines, you might be worried about memory footprint. So before I dive off into the memory footprint, first of all, how would you optimize a JavaScript application? The most important thing, first of all, is to find the actual hotspots. Find what is important for your application. Performance-wise, that would be functions that are worth being optimized because they're executed often, frequently, a lot of times. Memory-wise, that would be finding objects that dominate the heap, that are omnipresent in the heap, and that live long or that have a bad memory layout. But once you've found the actual object that's causing the problem, you need to understand why it's actually causing a problem. So without understanding the actual problem, there is no way you can fix it. And then you fix it. And the last item is really just that, fixing it. So here is my very personal, very unscientific opinion of how much time you need to invest into these steps. So fixing it is really just that. If you understood the problem, getting rid of it should be easy. This talk is mainly going to focus about understanding the problem at hand. And since fixing is so easy, we will also do that. OK, so let's look at a few examples. And the three examples that I want to present here are object select tracking, array representation, and execution contexts. We will look at three examples in depth and discuss a few best practices how to improve hot code around those optimizations. The first one will be about how are objects represented in memory. Second one, how are arrays represented in memory. And the third one, how is your actual execution environment of some function represented in memory. Okay, let's dive into that. So the first thing, object select tracking. Most of you might have already seen this example, the famous point example, and how would this point be represented in memory. So please stick with me. I'm going to give it a different spin, this time with the addition of select tracking. So let's go through that application step by step. And I promised I tried to do this without assembler, so I just have fancy graphics explaining it, no assembler code. I hope that's okay. So the first thing when we execute that constructor is we actually allocate the object in memory. You probably know that we have a hidden class system behind all of that, because JavaScript in itself is a very loosely typed language, and to really optimize for certain objects, we need to have a more precise type system behind it. So we invent our own types and call them hidden classes. And we just give that new object a little bit of slack. So in this graphic, that would be 4 slots that are available directly in the object. So there is no indirection going on here. You don't have a backing store where the actual content will be stored. It's directly in the object that also serves as an identity. So let's add the first property. That would be x. We add it. And since we now modified the object layout, we actually added a new property that can be accessed. We also need to transition the hidden class. So it's now a new type in our type system. And we remember that transition. So whenever we start from the first hidden class, add x, we will go to the next hidden class. And as I mentioned before, we store the value directly in the object. So accessing it is just loading one word out of the object, no indirection. Second step, obvious, add a new property, transition the hidden class again. So if you think of this transition chain or transition tree that you get on the right-hand side, you can imagine what would happen if you suddenly add these properties in a different order. You would end up with a different hidden class in the end. So that would be one point to avoid. Now let's repeat that with the for loop down there. So we get 2 objects that both have x and y. And now we have this fancy modification of the object that comes right after the constructor. So how would we deal with that? So every second object gets a set property. OK, we can just add that, no problem. We still have slack in the object. So both objects are actually over-allocated. We allocated too much memory for those objects. And at some point, when we have enough of these objects, we decide to basically freeze the transition tree. We say, OK, your application has allocated enough objects. They are probably going to look like this most of the time. So we are going to freeze that state and say, OK, those are the classes, the hidden classes that you're going to work with. Now, we actually want to get rid of the slack that we have at the end of each object. And we can do that. We just shrink the objects. The problem is every point that you instantiate with the point constructor can either have 2 or 3 properties. And we don't know how many. So we need to keep around at least 3 slacks in each newly allocated object. And that means for half of the object, we waste that memory. It's really wasted. So that's probably bad if that's a hot object, meaning you have like 1 million of those objects floating around in memory. That would be pretty bad. So we hopefully understood the problem now. How can we fix it? Well, fixing it is easy. Just use 2 constructors, meaning you come up with 2 transition trees or transition chains, and both maps can be optimized for their object size. So that fix is pretty easy. And so I left the implementation of those 2 constructors, point 2 and point 3 out. You can either implement them directly, which means you have some duplication in there. You could use some frameworks that are out there, like the prototype framework, all types of inheritance. You could even use, from within point 3, you could call the point 2 constructor by using point 2 call this and pass the arguments through. That would all work. The object layout would still look like this. The important thing is use 2 different constructors. Tell the VM that you actually are dealing with 2 different types here. So I said we should measure it. I hacked this pattern into a ray tracer, which deals with about 600,000 points, and up to 3 wasted slack slots in the objects and keeps them alive in memory. And that's the improvement that you get out of it. And those are 40%. So 40% less memory that your application consumes, which is quite okay, I guess. So now, since if you don't want to think through all of this every time and come up with the actual representation that your object is going to be in memory, I will give you a few best practices that you can follow, and that will hopefully allow you to write applications that are both extremely fast and slick memory consumption-wise. So first thing is try to initialize all properties in the constructor. And as I mentioned before, add all the properties in the same order, because otherwise that would screw up our hidden classes. And avoid object layout modification after the fact, so after the constructor has come up with the initial object layout. Now, this might sound like I'm taking away a little bit of freedom from the expressiveness that you have in JavaScript, but let me tell you a story about that. So I went to this pub recently, and at the entry they had this sign, and it said, "This pub serves food that is good, cheap, and served fast. You can choose 3. You can choose 2." And that kind of reminded me of this. So you have performance, speed on the one hand, then you have memory footprint on the other hand, and then you have the expressive power or the freedom that JavaScript gives you. And I'm not claiming that those 3 are actually all the time mutually exclusive, but knowing about those 3 points in the triangle, understanding it, and knowing where you're located in this triangle might help you to write better applications. Okay, so let's move on to the second example, array representation. So far we only talked about named properties. Now it's going to be about index properties. So again, we have something that is used as a constructor, or that used as a factory to instantiate arrays. And again, it's a hot method because it's executed several times. Thereby the array it produces is a hot object and might make up a bulk of your heap. So the first thing we do here is we actually instantiate a new array. For arrays, we want to have an object that represents its identity. That would be the small box at the top. That also stores the length, so how many elements, how many index properties do you actually have in that array. And we over-reserve the backing store again. So we again have like 4 entries that we can fill up after the fact without resizing the actual backing store. So we can do that. We add the index property with the name 0. We add the index property with the name 1. And now we add another property that's actually a double value. So that backing store is intended to store integers, or small integers actually. So now that we store a double into it, we actually want to have an efficient representation of that backing store. Efficient performance-wise. That means we actually want to unbox those doubles in that backing store. That means we have to change the layout of that backing store. And we do that. It's now taking 64-bit words, and that backing store is able to store doubles directly in them. So as you see, the 0.5 is stored directly into that backing store. That means we have to convert all the previous small integers into actual doubles now. That conversion takes a bit of time, takes additional memory, but that doesn't matter that much because the old one is no longer referenced and can be garbage collected. So, and next, we store an object, the true value in that backing store that's represented as an object. And that means the work we just did was bogus. We have to go back to the old representation again, 32-bit, and now we actually need to box the 0.5, the double value, which again means we have wasted a few cycles by converting back and forth, allocated a new backing store again, and collected a bunch of hidden class transitions that track those transitions. So if we generate lots of these arrays, it's gonna have a bad performance, and also you see there are a lot of backing stores which actually contain the same values. So that doesn't look very efficient, neither performance-wise nor memory-wise. So what would be a possible fix of that? Possible fix would be to not use this strange construct at all, but use an array literal. With an array literal, V8 can basically infer the optimal representation of the backing store, allocate that right away, and the most important thing, we can share the backing store between the arrays. And those backing store is now becoming a copy on write backing store. That's what the cow should indicate. That means we can share the backing store as long as you don't modify anything that's stored in it. As soon as you start writing to one of those backing stores, it will be copied and modified. So all the other arrays will still share the backing store. And this change should give you a performance boost and a memory boost. Awesome, right? You can have best of both worlds. And again, there are a few easy things to follow here, which should allow you to avoid this kind of trap. The most obvious one is if you use the array, if you're able to use array literals, try to use array literals. They're really awesome. We can generate highly optimized code for it, and we can immediately come up with optimal representation in memory for it. Pre-allocate small arrays to the correct size. So that basically means pass, if you know the size ahead of time, pass it to the constructor. And most importantly, try to use arrays to store only one kind of element in it. So especially try to avoid mixing object values with double or integer values. Okay. The last thing is about the execution context. So JavaScript is a functional language, and what that means is that on one hand you can have so one thing is functions are first class objects, so that means you can pass them around as in variables. You can have nested functions inside each other, and they have a proper lexical scoping, so that means the inner function can reference any variable that's declared in the outside function. So what does this mean in this example? We have an auto function make closure with two variables in it, large value, small value. So obviously large value is going to be the bumpy one. We have two inner functions in it and closure, and both reference some of the auto values. And then we call this function make closure several times. So what does this actually mean? Since the inner functions reference variables from the outer functions, we need to preserve that execution environment in some way. So it needs to be stored in memory. And the way we do that is we have a context object that's actually a heap object that's allocated on the heap, and we put the values that are basically going to survive the execution of the outer function in there. So arguments can be context allocated, in this case the size argument, because it's used by a nested function. So should the nested function init escape that outer closure, we need to preserve that execution environment. Same thing applies for variables. They can also be context allocated. They're also going to be put into that context. And as I said, this context is going to be referenced by the nested function. So this context is the execution context, the execution environment for those nested functions. So they're going to keep it alive until as long as they itself survive. So what does that mean? If one of those functions dies, like the init function, it's going to go away. But the context is still alive because it's referenced by the closure function, which escaped the outer function. And the large value can be some huge object, some huge array, which is basically the bloat in your application. And you want to get rid of that. So how would you fix that? Easiest solution, just get rid of that large value context allocated variable. Move it into the inner function. That's the easiest way. Thereby you got rid of the context allocated variable, and the closure function will no longer keep alive the bloat. So again, I wanted to measure this, and measuring this, giving a percentage here is just pointless, basically. Most of the application developers will just consider this to be a leak. So understanding this construct, understanding this way that the V8 context allocates variables and that functions can keep alive whole contexts might allow you to fix severe memory leaks in your application. So here are, again, the basic best practices. The first and most important thing is you should be aware of context allocated variables. So you should be aware that these things exist, and ensure that hot closures, so basically closures that you generate often, have a small outer context and move variables as deep as possible into the nested functions, thereby avoiding those leaks. So we just got rid of all the bloat, and hopefully this allows you to write applications that don't introduce memory bloat, that are performant after all, and hopefully this might also apply to other virtual machines, because so all the examples I gave are highly targeted for V8. So they discussed how V8 represents these objects in memory, but I guess the same optimizations could be applied in other VMs. I cannot judge that, but it should allow you to drive all of your engines safely and have a free highway like this. So with that, I want to thank you very much for listening in. Thank you. So I hope I could convey some of the basic concepts how V8 comes up with representations of objects in memory, and how to avoid some booby traps that are hidden in there, not intentionally. If you want to know more, either ask me now, because we have lots of time, and you can also find me in the during the breaks at the Google booth, or contact me directly. So if you have questions, shoot.
I've got a question about hidden classes. So
yep.
you said you would prefer if people would create instance variables in constructors.
Yes.
Does that also work if you do something like object.prototype.variable name equals something or other?
So if you store an property on the prototype of an object, that means it's actually going to be stored in a different object that's referenced through the dunder proto field, as I learned yesterday, so whenever we access that property, we have to follow that dunder property field and then access that object. But the representation of that object, same rules apply there. So how you come up with that representation is, again, follows the same rules. So probably the prototype object that you use for this object is going to be shared among several objects. So most of the time, the prototype objects aren't hot in a sense that several of them exist on the heap. They are just hot because they are used often. So they should have a performant implementation, performant memory representation. But if you waste some space in there, it's probably not that important.
Thanks. So I wondered the example where you had two different representations. So at this point here, and usually if this object is hot, it's used very often, and
Yep.
and V8 is much faster if it's monomorphic. So my general advice would be to say only have one class that has 3 fields, and if you don't use the Z field, just put undefined in, and you will be just faster. And I mean, it's 32 bits. Okay, yes, it wastes a little bit of space, but
Yeah,
compared to the
so
speed.
You obviously understand the problem at hand. I hope I could teach that general underlying problem to more people, but knowing about this trade-off, either waste space or have a monomorphic object, brings you forward in a huge step.
Okay, and then a second question was this inner functions. So when you have a nested function inside your, the init
Yep.
function, for instance, you have to run through the whole function to see what variables are captured or in the nested function.
Yep.
Why not also see if the init function itself is actually captured itself or leaves the scope? So in this case, it's called from within the constructor, so you know it's not going to capture any variable.
Yeah, you would need, so,
call it
I mean, in this
somewhere
example, you could
differently.
just say, okay, I see it right. I look at all the code and see it. But it requires escape analysis because you need to find out whether that function escapes or not.
Well, but you're already looking if something is kind of a, you have to see if large value is inside the init function, so you just keep tracking the init too, so it doesn't seem that difficult. You just, if init is used in a non-calling function context, okay, then just say we need to capture everything in there, but that doesn't look that difficult. It's not really a difficult analysis.
No, it's not. Maybe it's not a difficult analysis, but the problem is you need some optimizing compiler for that, and the layout of the contexts. You need to get them right the first time. So when you didn't optimize the function yet, or otherwise transition that context layout somehow if you optimize a function, because you already created some instances of the function object. They escaped into your heap. They're floating around, and now you decide to optimize this whole mess, this whole make closure thing, and you come up with a better representation. But there is already the bad representation out there. So if we could, if we crankshift everything, then we would be smarter about that. But then startup performance would suck. So again, classic trade-off.
One more quite detailed question. You were talking about allocating and assigning all the properties in the constructors so that you can presumably allocate the precise amount of space in
Yep.
the object itself. How accurate can you be in that? Can you really determine precisely how much to allocate, or will you ever have to spill to the separate slot array?
The perfect scenario from a VM implementer point of view is if you just have simple this assignments in the constructor. So if your constructor looks like this is, we just look at that code, see during parse time, so no optimizing compiler, we see the layout there in the code and just boom, come up with the optimal representation. And when we optimize that function, boom, inline that, know how it looks like. So that's the optimal way. But that takes away a lot of freedom from JavaScript developers.
Right. I was asking about the more complicated case where you might have some branching or whatever, which might create different layout.
The one solution we use is this object select tracking. So we overall allocate all the time like this, and after we have observed fixed amount of allocations, we shrink the objects and seal their size if you want. So that gives us the most flexibility, even if you have non-simple constructors.
Great. I think that'll be it for now. Give a hand to Michael.
Thank you.